All right, hi everyone. This is going to be a video covering principal component analysis, focusing on a conceptual review of principal component analysis for EE16B. So let's get started. So let's first imagine a scenario where we're given a bunch of 2D points. So each point lies in the two-dimensional plane, and say it so happens that the points all lie on the line y equals x, which is equivalent to saying they all lie on the span of the vector 1, 1. Okay, so first of all, if we're given this data and we don't know this fact about the data, the fact that they all lie along this line, it would be useful to learn this fact somehow through some analysis, right? Because that's a very important property of this data. And second of all, if we were to know this fact that all the points lie along the vector 1, 1, then we could represent each point with a single number, that number being how much along the vector 1, 1 that point lies. So for a concrete example, so say this is the vector 1, 1. So then this point right here would just be, we could equivalently call it 1, because it's just 1 times 1, 1, the vector 1, 1. Whereas this point right here, we might say is like 2, because it's 2 times this vector. We scale this vector by 2 to get to that point. And perhaps this number would be like -3, because we have to flip this 1, 1 vector and then scale by 3 to get to this point. So it's useful to first figure out the fact that all the points lie along this line. And once we know that fact, we can represent each number instead of being a point in 2D space with just a single number, which represents how much along the vector 1, 1 we have to move. Okay, let's complicate the scenario a bit. Now say our points look like this. So just kind of by looking at the points, we see that they kind of lie along the same line, y equals x, but they're a bit scattered. In other words, there's a little bit of noise added to these points. So if we're trying to figure out patterns about the data, we'd still characterize the data as being pretty much along this linear line y equals x. We don't really care about this noise because maybe that just comes from bad measurements or from uncertainties in the real world. So we'd still like to figure out the fact, we'd still like to determine somehow that these points are mostly along this line y equals x, or mostly along the vector 1, 1. Okay, so we can also imagine a 3D version of this. So remember that points can be in like arbitrary dimensional space, but we're only constrained to visualizing 2 or 3 dimensions. But say now that we have points that are given to us in 3D space. So there's 3 numbers that represent each point. And say the data set looks like this. So there's an ellipse looking thing that lies in the XY plane. And the points are along that ellipse, mostly along that ellipse. And all the points are purely on this flat XY plane. They don't have any height. There's no Z direction. Okay, so if we're trying to do some analysis on this data, we'd like to know that A, the points vary most along the x-axis. What do I mean by that? I mean that the points are most different along this x-axis. Just by looking at the points, we can see that the most difference in the points comes from this component of space. They also vary a little bit along the y-axis. They differ in their y-coordinate, but not by as much as they differ in their x-coordinate. And lastly, they don't differ at all in the z-coordinate, right? Because all the points have the z-coordinate of 0. So the z-coordinate essentially gives us no information about the points. The x-coordinate gives us the most information because the points are distinguished most by their x-coordinate. And the y-coordinate gives us a bit of information, but not as much as x. So what we wish to do with PCA is formalize this kind of intuition about finding directions with most information and formulating the problem in a mathematical way that allows us to solve this problem. So let's do that. And the key ideas behind PCA are 1, projections, and 2, the idea of maximizing variance. So let's review these concepts because they're very important. So first is the idea of projections. So a quick recap of projections. So we typically write the projection operation as projection of a vector u onto the vector v. And the intuition is that you're trying to find the portion of the vector u that lies along v. So the common diagram that people see regarding this is, say this is our vector v in space, and this is our vector u. Okay, so then the projection of u along v is we're going to drop a orthogonal line from u onto v. So it's a right angle right here. And this part right here is the projection of u onto v. So mathematically speaking, the projection is typically a vector. And I'm not going to derive this. You can find this in like your EE16A notes. But it's going to be the dot product between u and v divided by the norm of v times v, except you have to normalize v. So this is called the vector projection. But another quantity that people equally care about is the scalar projection. Because a lot of times, and this is the case in PCA, we don't care about the vector. We just care about how much along the vector v we have to go. So we just care about this scaling portion. So that part, the u transpose v over norm v, is called the scalar projection. And this is a scalar number, so it's just like a number like 2 or 3 or -1. And it basically tells us, okay, how much along v. So we first take v, we normalize it. So we shrink it so it has norm 1. And then we scale it again by this quantity. And that gives us the projection. So it just tells us how much we have to scale a vector by to find the projection. Okay, the second concept that I'll review real quick is the concept of variance. So variance is a statistical concept, and we're gonna look at the scalar case, where we have a bunch of scalar numbers, a1 through an. What the variance formula is 1 over n minus 1 summation. So we sum all the points, sum over all the points, but what we're summing is the point minus the mean of the points squared. So this mu term is the average of all these points. Okay, so let's look at this formula and understand a little bit the intuition. The mean is fixed, right? So if we're given a set of points, they have a fixed mean. And what we're doing is we're taking each point and we're looking at how far away in kind of an absolute sense. So we don't really care about the direction or the sign. We just care about how far away each point is from the mean. And then we take the sum over all the points and then normalize by dividing by n minus 1. So the variance is a measure of how much a set of numbers deviates from the average. So if there's a big variance, that means that the points typically are very far away from the average. Whereas if the variance is small, then the points are very clumped around the average. So a nice picture is the number line. Say this point right here is the mean, and we have a bunch of data. So a high variance situation would be something like this. So the points are centered around this blue point, except they're scattered pretty far. But a low variance situation would be something like this, where the points are still centered around that blue point, except they're clumped much closer. So they're typically much more close to the mean. Okay, so now that we've reviewed some of the relevant concepts, let's get into the formal description of PCA. So what we're given in PCA is just a bunch of data points. That's it. Specifically, let's say we're given n data points and each point is in d-dimensional space. So d can be any integer number, 1, 2, a million, a billion, and n is an arbitrary integer as well, positive integers. And the goal, which we'll formalize a little bit more in very shortly, is to find the direction or directions In other words, the unit vectors, which capture the most information about the data. All right, the second part, the second thing that we need to formalize is what do we mean by most information? So what we mean by that is we want to find the vector that maximizes the variance of all the scalar projections of the data. So that's a lot of words and a lot of mathematical words. So let's look at some pictures because that's probably easier to analyze. All right, so let's look at this case where we're given like 6 data points, right? So the blue points are the data, and I've drawn a couple of vectors. So remember that in the sentence above, I just said we want to find the vector that maximizes the variance. So say we choose a vector and see what the variance along. So say we choose a vector and we look at the variance of the scalar projections of the data. So if we choose this red vector, then first we have to find the projection of the points onto the red vector. So how are we going to do that? Geometrically, what that means is, okay, let's zoom in a bit. We take each blue point and we drop the perpendicular component of the blue point onto the red vector. And then that corresponding point is going to be the projection. So what I've done on the right diagram is drawn every single projection of the points. So I think I missed a couple. So there's going to be one right here and then one right here as well. But in other words, all of these projections are going to be on this red vector. Okay, so that's one scenario. Let's choose a different vector, the green vector, and see what happens if we project everything. So if I do the same thing, I drop a perpendicular from each blue point onto the green vector here. What I'm going to get is this. So all of the points will lie along the green vector, and they're going to look like this. Okay, so let's look at what the variance in each scenario is going to be. In each scenario, the mean kind of looks like it's 0, right? The points are centered around 0. Same thing here. Except in the red case, all of the points are much closer to 0. They're clumped around 0 much tighter. Whereas in the green case, they're spread apart. They're more stretched out in each direction. So in this case, we have a low variance direction. So the red direction is low variance. In other words, each point is less distinguishable. They're all kind of the same in the red direction. And that makes sense, right? By looking at this part of the diagram, we can see that this direction is a direction that the points are pretty similar in. However, if we look at the green direction, that's a very high variance direction. In other words, the points are much more distinguishable. They're much more different along this dimension than they are along the red dimension. Because we want to characterize the points, we want to make the points as different as possible, right? Because if every point, we don't like it when every point looks similar because there's nothing interesting about that data. Whereas if all the points are different along the dimension, that allows us to make some sort of analysis about the points. For example, we can group the points in a certain way, or we can cluster them. So that allows us to do much more interesting analysis. So our goal is to find high variance, and we don't like low variance. Okay, so let's actually get into what we do in PCA. Again, keep in mind that the overall picture is that we're trying to find the vector that maximizes the variance of scalar projections. Okay, so the step 1 of PCA is to center the data. All right, what do we mean by center? Centering means, let me write this down. First, we find the mean of the points. So remember that our points are x1 through xn, and they're all vectors in d-dimensional space. The average of these points, which I'll call x bar, is also a vector, and it's the standard average formula. You sum the points, and you divide by the number of points. So what the centered data is going to be is, again, a bunch of data, d-dimensional data, and I'm going to call them x tilde. So each x tilde is going to be the corresponding point minus the average. And let's look at why we're going to do that. And again, I'm going to use a picture. All right. So say I have this situation where I'm given a bunch of data in this scenario. And it's very similar to what we've been looking at, except all the points are shifted down. So the y-intercept of the line that they lie on is like -1 or some negative number. So the average of these points is not 0 now. They're centered around like the vector 0, -1, for example. So let's just call this vector 0, -1. Okay, remember again that our goal in PCA was to find the vector that maximizes the the variance of the scalar projections along that vector. So in all of the diagrams, what we did was we kind of drew a vector and then we projected onto those vectors, onto the points onto that vector. However, if our mean is offset, so it's not 0, then it doesn't really make sense for a vector to really represent the points at all, because the vectors must start at the origin, right? So if I were to choose a vector such as this one, well, it has no chance of really representing the points because the points don't even go through the origin, whereas the vector, any vector, always does. So in order to solve this kind of initial problem, we're going to do a pre-processing step where basically we find the mean, in this case, 0, -1, and we're going to shift all the points so that the mean of these shifted points is 0. So in this case, we would subtract 0, -1 from every single point, which effectively scales each point, or sorry, not scales, it shifts each point up by 1. So now the y-intercept of the points is 0. In other words, the mean is 0. So now if I'm going to try to find a vector that represents these points well, which again is the goal of PCA, well, now we have a really good chance of that because the points go through the origin and the vectors go through the origin. Before there was a mismatch issue where the points did not go through the origin, but whatever vector we're trying to find does. Okay, so this is a very important step. Always remember to center your data. Okay, now once we have our centered data, what we're going to do is, again, the goal is to find a vector v, then maximize the variance of the projections. So let's look at what happens if we fix a vector v. So say instead of having the choice and trying to find the best v, we only have one v that we care about. And we'll just call this v. And typically, we want the norm of whatever vector we find to be 1 because we just care about the direction. We don't really care about the scaling on that vector. So once we fix v, let's find the scalar projections of each of the center data points onto v. So remember that the formula for projection, so if I'm going to project xi tilde, so the center data point, onto v, what I'm going to do is the dot product between the two vectors over norm v. So this is the scalar projection. Except remember that we restricted the norm of v to be 1, so this is just going to be the dot product. Okay, so what we're going to end up with is a bunch of scalar numbers, where each scalar number is just a dot product. So x1, x2. So we take all these dot products, and now we have a bunch of scalar numbers. And now we need to find the variance of these numbers. But remember that in the variance formula, we need to find the mean first. Now, the really nice thing is that because the x tildes all have 0 mean, the projections right here are also going to have 0 mean. So to see this, let's actually compute the mean. The mean is 1 over n summation of xi tilde transpose v. So by inner product properties, we can pull out this v because it's common. So it's kind of like a distributive property, and then look at the sum. Okay. Well, remember that these are the demeaned points. So these have 0 mean. So that means that if you add them up, this is a tilde. That means that if you add them up, that vector is going to be 0. So this is going to be 1 over n v transpose 0. And if you take the dot product with the 0 vector, you're going to get 0. So that means that we just showed the mean of these scalar numbers is 0. Okay, this means that if we look at the variance of all of these projections, so the variance of x1 tilde transpose v, x2 transpose v, so the variance of all these points is going to be, recalling the formula for variance, 1 over n minus 1 summation of xi tilde transpose v minus the mean squared. So luckily the mean is 0, or not luckily, we made it 0. So then what we're going to have is xi tilde transpose v squared. Okay, so remember that xi is a vector and so is v. So let's write this in matrix vector form. Okay, and the way we're going to do this is we're going to define this big matrix X, which is our centered data matrix. So the rows of this matrix is going to be each data point. So specifically, it's going to be a n by d matrix. Okay, so if we compute the vector now, so if we take the vector x times v, by matrix vector multiplication rules, this is actually going to end up being x1 tilde transpose v, x2 tilde transpose v, xn transposed tilde transpose v. So this is going to be an n by 1 vector, and the vector is going to be of the projections. So remember that in the variance, we want the sum of squares of each of these. So sum of squares, that kind of sounds like the dot product of a vector with itself, right? Because that's exactly what that is doing. So if we take so remember that this is just a vector. If we take the dot product of that vector with itself, then what we're going to do is we're going to take each of these components, square it, and add them up. So if you write that out, this is what you'll get. The summation of all squared. You'll notice this quantity exactly, except all we need to do is take care of this 1 over n minus 1. Okay, so that means that the variance of our numbers, so the variance of x1, so the variance of all of our projections is actually going to be the quantity 1 over n minus 1, so we're bringing back the scaling, times xv transpose xv, and using the transpose rule. So the transpose rule I'm mentioning is that if we have two matrices or vectors, and we take the transpose of their product, this is the same as flipping the order and taking the transpose individually. So if we use that, this is going to be v transpose x v. Okay, so that's actually a really nice formula for our variance. Now let's take a step back. Remember that in this kind of derivation, we fixed v. However, in the PCA problem, what we're trying to do is we're trying to find the best v, and we're trying to find the v that maximizes the variance, right? So we have a bunch of choices for v. We want to find the one that maximizes the variance. Okay, so we found that for any given v, the formula for variance is this. So let's write down the maximization problem. So we want to find the maximum. So we want to choose the v that maximizes the following quantity. So we want to maximize v transpose xv. But in the whole previous derivation, we limited v to have norm 1. So let's parse this a little bit. What this is saying is that Okay, out of all the choices of V, such that the norm of V is 1, we want to find the one that maximizes this number, specifically 1 over n minus 1, V transpose X V. And the reason why we want to maximize this number is because that is the variance of the projections of the data points along V. Okay, so if we're trying to maximize a number, we don't really care about the scalar in front of the number. So this can be equivalently written as maximize, so find the V that maximizes the number just V transpose X V. And this maximization problem, so finding the V that maximizes this quantity, is exactly what the PCA problem is. All right, so let's do a quick recap before I end this video. What the setup that I initially said was that we're given a bunch of data points, and we want to find some sort of analysis about these data points. For example, if it so happens that all the data points kind of lie along this line, we want to figure that out. We want to know that fact about the data points. Similarly, if we're given a higher dimensional space of data points, we want to determine, okay, along which directions are the points most different? Which is an equivalent way of saying that is which directions in space maximize the variance of the points. So we reviewed the concept of projection and variance, which are really important. And we kind of set up the problem so that what we want to do is we want to find the vector out of all the possible vectors that maximizes the variance of scalar projections of the data. So this example is super useful to kind of understand that. We find, if we choose this red vector in this data set and project everything, then we get this set of data. Well, the variance is small because the data is clumped around the mean. Whereas if we choose this green vector, then the variance after projecting is large. So the points are more different along the green direction. So now the question becomes, how do we mathematically find the green vector? In this, like up till now, we were just kind of looking at the data, but now we want to find a mathematical way to do this. And that's what we did in the end of the video, where we figured out that first we need to center the data so that both the data and the vector we are finding can go through the origin. And then we found that if we fix a V, the variance of the points can be nicely represented as this formula. Except now we want to find the V that maximizes it, right? So out of all the possible choices of V, such that the norm is 1, we want to find the one that maximizes this quantity. And that's the final PCA problem. So I'll go over how to solve this problem in the next video. And thanks for watching.